Administrator has said many times about potential missions for the moon base is the science. And we deploy detectors jointly with NASA in space right now. And we're looking at sending out a request for information, an RFI, to the university community to see if any of the detectors that are potentially out there for mapping the universe might make sense to deploy on the moon, at the moon base, where joint science by NASA and DOE could happen. And then the last one that I would mention that it's a kind of a narrow topic, but quite exciting to me personally. One of the things that Congressman Lucas has been a leader of passing out of Congress was the National Quantum Initiative, of taking a look at quantum physics for application for quantum computing and quantum communications, and building out quantum networks to build out a second internet and based on quantum mechanics is certainly possible. And we're putting significant dollars into that. We just announced $1 billion 2 weeks ago. And one of the areas that certainly would be very interesting is to launch a satellite for quantum communication relaying for entanglement and repeating. That's an area that both NASA and us are highly interested in. So those are just a few of the examples of the sort of things that we work on together. It's a truly exciting time, and we look forward to broadening that conversation with the broader community and see what we can do together.
Awesome. All right, thank you, sir. And with that, I'll pass it over to the administrator for his opening remarks.
Well, thank you, Anthony. Ranking Member Frank Lucas and Undersecretary Paul Dabbar, President Janet Leavitt. What an honor to be here back in Oklahoma, actually having a meeting with people rather than just with a computer screen. This is a breakthrough for many of us here. You know, we've traveled to launch rockets, we've traveled to do these things that NASA needs to do, but you know, the days of the meetings have kind of gone away, and it's actually good to be in a room with people, and we're thrilled to be back with people in the city of Tulsa, my hometown. So it's good to be here. I think Dr. Dabbar, you pretty much gave the laundry list of the partnership, but I cannot emphasize enough how important that partnership is to America's space agenda. You mentioned, a lot of the missions where we need to work together. I would say photovoltaics is probably a critical piece of that. When we think about all the missions in orbit around the Earth, all the missions at the moon, the missions at Mars, we just had this amazing discovery yesterday. Phosphine, of course, it wasn't, it was the Royal Aeronautical Society, not NASA, but what an amazing discovery. About 10 years ago, we found life at 120,000 feet in the Earth's atmosphere. So the idea that phosphine, which is a byproduct of anaerobic life, is being found in the upper altitude of Venus is significant, because we don't know any other way phosphine is created. So this is exciting, but the point is this: we go to Venus, we need solar power. Solar power and photovoltaics are critically important. Once we get past Mars, though, it gets really difficult. At that point, we have to have partnerships with DOE when it comes to radioisotope thermal generation, basically using nuclear decay to create heat and then using that heat to create electricity. And we've had so many great partnerships throughout the years to achieve what we have now explored every planet in the solar system. And that's because of the great partnership with DOE. Within, inside of Mars, Paul is right. We're going to need nuclear power even inside of Mars, because about 10 years ago, we found on the surface of the moon we found water ice, I should say. We found water ice. Hundreds of millions of tons of water ice. What does that mean? Water ice is air to breathe. It's water to drink. It's also hydrogen, which is rocket fuel. It's the same rocket fuel that powered the space shuttles. It's available in hundreds of millions of tons on the moon. So the question is, we got to get to the moon, and then we need to set up the lunar base, and we need to get to the water ice. We need to characterize it. We need to separate it from the regolith. Then we need to crack the water into hydrogen and oxygen to create the fuels of the future on the surface of the moon. The challenge with Earth is we have this really big gravity well. So getting fuel into space is very difficult. The value of the moon is that it doesn't have a big gravity well. It's 1/6 the gravity well of Earth. And the value of the moon is that it has no atmosphere. So you don't need all the fancy aerodynamics to get off the moon. In other words, we could actually use the fuel that we create, in fact, on the moon. I know it sounds science fiction, but it is not that far away. And in fact, we are developing missions right now to go get that water ice and characterize it for future missions that could do just what I'm talking about. So this partnership, and so this is going to require nuclear. That's what the Krusty mission, Dr. Dabbar, that you talked about, the Krusty mission, that's what it's all about. Getting that nuclear fission, in this case, to the moon, so that ultimately we can have enough power to do those kind of activities. So those are all very exciting things. Right now, we're commercializing low Earth orbit. Many of you have seen, we launched American astronauts on American rockets from American soil. We're doing it commercially. We're partnering with private industry. NASA wants to be a customer. We want to be one customer of many customers in a very robust commercial marketplace in low Earth orbit. We want to have numerous providers that are competing against each other on cost and innovation to drive down cost and increase access. And so we've done it now with resupplying the International Space Station. Now we're doing it with crew to the International Space Station. The next step is to commercialize space stations themselves. Right now on the International Space Station, we're proving that we can compound pharmaceuticals in a way that you cannot do in the gravity well of Earth. And I want to say thank you to Ranking Member Frank Lucas. He's the ranking member of the committee that enables and encourages and makes all of these missions successful. But it's going to change life here on Earth. The compounding of pharmaceuticals, creating immunizations for salmonella, creating immunizations for pneumonia, and advancing these kind of immunotherapies. And then ultimately, right now, we're proving on the International Space Station that we can, in fact, use advanced materials to create, for example, an artificial retina for the human eyeball. So people in the future who have macular degeneration don't have to lose their eyesight. And these are things that are going to require partnerships. What I love about this room, we have industry here, we have academia here, we have government here. And I'm going to quit talking here in a few minutes, but what I'm looking forward to is kind of a virtuous cycle of dialogue among as Representative Lucas said, the brilliant people here, and figure out where we can find these partnerships, where we can collaborate and achieve some really stunning developments. On the International Space Station, we're also, if you can believe it, we're working towards a day where we're going to print human organs in 3D. We're going to use Dr. Dabbar. There's going to come a day when we could use your own skin cells to get your own adult stem cells and create organs that are made perfectly for you. And you can only do that in the microgravity of space, which is the value of space in general.
Would that help me with my Ironman time speeds with a better new heart?
It could, but you might get disqualified. But my point is, right now, all these things are happening on the International Space Station. The future is, think of a dozen space stations in orbit around the Earth that are all commercially capitalized with academia, researchers. Right now, we're moving forward with private astronaut missions using suborbital space. Very soon, we'll be using orbital space. So there's a lot of bright hope here. Of course, we got the moon program. We're going to Mars and beyond that. Real quick, as I close out, I want to talk for a second about what I see here at the University of Tulsa. And there's some amazing people in the room. But I think I'll start with photovoltaics. The idea, that we're getting more energy conversion and more efficiency in that conversion than ever before means that the future of photovoltaics is very different than the past. And now those photovoltaics, yes, it's new materials that is making this happen. So we think about gallium arsenide, which is this material that has a much higher conversion rate, but it's also exceptionally expensive and difficult to create. And now we're talking about layering they call it multi-junction solar cells, where you have multiple different layers of different types of material that can bring together all the value of the entire spectrum of visible light, so that we can increase the energy conversion with these multi-junction solar cell capabilities. And here at the University of Tulsa, with Dr. Hari, taking those capabilities and then saying, okay, how do we get even more energy out of the light? Well, you've got infrared and you've got ultraviolet. Can we convert that into visible light so it can be used by a solar panel? And what we're discovering is that yes, we can, which means we can get even more efficiency out of these solar panels. And the University of Tulsa is working on that every day. And then on top, and I know you're going to correct me when I quit talking, and that's okay. But then on top of all that, there's even more. We think about the fact that we can converge, focus the energy of the sun in different ways onto these photovoltaic cells and get even more capability. So this is important for space because what we care about in space, and Dr. Dabbar, I know you've got a lot of research into this as well. What we care about is how many watts are we getting per unit mass? How many watts are we getting per unit volume? These are the things that have to drive down our cost. The problem is once we get to that position where we're driving down the cost per unit watt, we're getting the most wattage per unit volume, the most wattage per unit mass, it becomes very, very expensive. And the materials and the material science necessary to achieve this, in many cases, might not be produced in the United States of America. That becomes a national security issue for our country. This is not just about energy, clean energy. This is about the national security interests of our country. We think about the satellites that are in space that are detecting in infrared missile launches all around the world. We think about the satellites in space where we do nuclear command and control. It is important that our country, the United States of America, have the ability to get the materials and the science necessary for national security. That's what the Space Force is all about. That's why I was so thrilled to hear that Skydweller could come, because I know this is near and dear to your heart as a company that builds airplanes dependent on photovoltaics. So I think that is a huge area where the University of Tulsa can partner with the Department of Energy, can partner with NASA, and make sure that the United States, this is what the Space Council is all about. The Space Council is about making sure that the United States of America is preeminent in spaceflight. And this is going to be necessary for the future. And we need to hold on to these capabilities right here in this country. Finally, I want to talk about aeronautics, because that's going to apply to Skydweller as well. We need to get really good at integrating unmanned systems into the national airspace system. Dr. Lloyd Hook worked at NASA for many years. He was part of a team that won what's called the Collier Trophy, which goes to one team every year for the greatest advancement in aeronautics. And in 2018, for the first time in history, it was given to a project that was software. And of course, he's an electrical engineer, computer engineer. You can tell us what your official title is, whatever it is. Bottom line is, you're looking at the guy that made these kind of things happen. And when he did it, they won the Collier Trophy for what's called GCAS, the Ground Collision Avoidance System. It's actually auto GCAS. So when your pilot is incapacitated for whatever reason, the plane will fly itself away from the ground. But it won't do it before the pilot is ready. If the pilot is in control, it won't take over before the pilot is incapacitated. But as soon as he's incapacitated, or when the risk is sufficiently high, it will fly away. And it has already been responsible. This is why it won the Collier Trophy. It has already been responsible for saving the lives of 10 military pilots. 10. And that guy's sitting in this room right now. That's an amazing capability. NASA brought that to the table. We're thrilled that Dr. Lloyd Hook saw fit to stay in a field where he can continue to work on these very important programs. The next step in that auto GCAS is integrating unmanned systems into the national airspace system. There's a process by which that can happen. And of course, I'm thrilled that we have folks from the FAA that are also paying attention, because integrating these systems in the national airspace system is a regulatory challenge that we're going to have to work through. NASA wants to be a partner with that. NASA needs academia to partner with us so that we can partner with the FAA. So I think there's amazing talent in this room doing astonishing things, for the Department of Energy, for NASA, And now for industry. And of course, we're very excited about many of these things. And what I'd like to do is just, like I said, open up a dialogue about what can be done, what should be done, how universities, not just the University of Tulsa, but in general, how universities can support the NASA mission and the DOE mission, and the kind of things that we're looking for as agency heads as we move forward for our nation. So with that, I will turn it over back to you, Anthony.
All right, well, thank you, sir. So yeah, I kind of want to just start off and just open it up for an informal discussion, kind of build off what the administrator was said, kind of talk about the cooperation between the two organizations and the long-standing cooperation that it's had for years. So whoever wants to kind of kick it off, you can go ahead.
Robert?
Yeah, well, thank you for those comments, because SkyDweller agrees with those 110%. You know, we're developing the first commercially viable pseudo satellite, and the power of that is going to be photovoltaics. Okay, and it's very important to us. We have a 236-foot wingspan aircraft, so the surface area is quite large. If you look at the gallium arsenide worldwide production, okay, if we're marginally successful, we're going to move that market. And we don't want to buy solar cells that are, from China, okay? We would want to buy them here in the United States. And it's important because wherever we buy those, we're going to move the market. And so those people are going to have a massive amount of production capability, which is going to drive down their costs, which is going to make them win even more work in the spacecraft business.
So you're worried about they're going to have pricing power? Is that the deal?
Yeah, and we do not want to have,
Right.
pricing power in the Chinese hands over us.
Right.
And that's our position, at least. It's SkyDweller.
Yeah, no, that's good.
Yeah, I mean, if I can comment a little bit about the history of solar and economics, and completely agree, Robert, with your point. So, there was a great program at DOE, funded a lot in academia and the labs around a program called Sunshot about 10 years ago. Sunshot was a real push to fund R&D to drive down solar costs. Depending on where you started, it reduced solar costs by 90 to 99%, kind of depending on what your start date was, right? A significant shift, and that has obviously led to applications for solar that is, orders of magnitude above where it was 10 plus years ago. So the technology jump was quite successful. The U.S. taxpayer put a lot of money into that to do that. That was a great success. The failure was that most of these panels are not being made in the United States. So if you're thinking about it from a supply chain point of view, if you think about it from an investment of the American taxpayer point of view and the American worker point of view, that was not a win, to be direct. Technology win, supply chain and jobs not where it should have been. And so I agree with your point that when we start developing the next layer of beyond lithium ion batteries or perovskites and solar or whatever the next technology jump is, that the focus should not be just on the S&T. The focus should concurrently be about supply chain, manufacturing, and usage so that we don't miss that opportunity. You bring up a good point about next generation solar. We're also doing this on batteries because there's somewhat similar issues around lithium ion, and we should be doing the same thing for beyond lithium ion chemistries. And we have been, Connor, who works on commercialization, can talk about this, but I completely agree with you, and we should make certain that the federal footprint doesn't ignore the commercialization supply chain concurrently with the technology maturation.
So go ahead. No.
Yes, sir. The one thing I'd add to that is this is a perfect opportunity to remind everyone listening in academia and industry, we need your input. One of the programs that Undersecretary Dabbar was just referencing is our Energy Storage Grand Challenge. And one of the things we're putting in at the very beginning of this project is a tech transition roadmap and plan going forward so that we're not waiting 5 years and then saying, well, now we've got some great basic research. How do we actually make it have an impact? We're building it in at the beginning, but we need input from academia and industry throughout the process.
So,
I think it's more than just the S&T though. You need to worry about where they're gonna produce it. I mean, we talk to everybody who's making high performance batteries. Okay, lithium metal, lithium wire, you know, the metal wire, all these different technologies. And, you know, yeah, we'll get the prototypes here, maybe in the US, but we need to make sure that the long-term production stays here. Because that's a,
And to that point,
We're not hearing that.
our slogan for the Energy Storage Grand Challenge is research here, design here, build here, sell everywhere.
yeah, and I do think there is the tech transfer piece that's where it absolutely has to start. I think probably for us as leaders in the nation, we need to be thinking of generational leap ahead kind of technologies.
Yeah.
And those generational leap ahead technologies that we want to invest in are going to come from the national labs and in fact, probably from universities with, you know, either, you know, contracts with the national labs or contracts directly with agencies. Now, the universities, like the national labs and like, you know, NASA centers, need to have a very robust program to disclose when you have a discovery and get it patented through, you know, the different patent offices and then be, you know, we have it in our charter that we are to take the technology that we develop and make it as broadly available as possible. And the reason, and that's what tech transfer is all about. That's why you patent it to begin with, so you can license it and get it out to the public. And in fact, benefit lives here on Earth. That's our goal at NASA. A lot of people don't know that. Our goal is to benefit lives here on Earth. People are watching this probably on, you know, internet broadband from space. That's the benefit of what NASA does and develops. So I think tech transfer has to be a big piece of it. Doing that right is the first step. But if we are doing that right and it's a generational leap ahead technology, I think there are tools that we would use to make sure that it stays in the hands of the United States of America. And I think that's got to be the key.
Yeah, I think it's a better use of our effort rather than, you know, necessarily trying to reclaim some technology production that's already occurred. Exactly what the administrator just said. Let's just go ahead and, you know, I think really focusing on the next generation that's going to jump the performance characteristics of some of those existing ones, and you were talking to some of them, and because it's A, that's going to be the next generation technology already, and B, it's easier to be building it because we're not, you know, because we're starting the technology here, right? And I'll give a battery example rather than solar here real quick. So the beyond lithium ion battery chemistries, so not lithium ion, but sulfur, lithium metal, you mentioned, magnesium, solid state versus, you know, liquid electrolytes, you know, have a possibility of having 300 to 500% improvement above lithium ion. It's material enough to have a technology shift at that point, and or the inverse of that for cost reduction, right, through different materials and so on. And so, you know, really focusing on the S&T, but concurrently with the S&T, with the jump, extremely material jump in performance, is that concurrently, as Connor was saying, concurrently with the S&T, finding who's going to build it and build it here with American workers is quite a bit of a focus of, but I hear your point. I mean, we just need to be able to drive those harder. I think us as a leadership team, I've heard this, you know, when I joined the leadership team here a few years ago, where, you know, when we were asked, Jim was probably asked the same thing, is like, want to make certain that, you know, not only do, you know, leaders here in different discovery areas of the government have a background in either aerospace or nuclear or so on, but have a business exposure. So it's not just about the discovery, it's not just about allocating dollars, but it's also about how we can integrate with the commercial sector to do exactly what you're just saying.
It's an important point. Dr. Hari, I know you've got some thoughts on I want to hear your thoughts on photovoltaics. What is the next big leap ahead that we need to be thinking about?
In fact, I was speaking with Robert and I told him now, we can overcome, there's a fundamental limit for the efficiency of solar cells. If you are looking at conventional solar cells like silicon and gallium arsenide, that's called the Shockley-Coursier limit. That's the theoretical limit of about 30%, that's all. But as you mentioned, if you use new materials, we can overcome that limit. We can go up to 45% or 47%. We can go up to that.
Yeah.
So
when you do that.
Yeah.
The watts per gram go way up.
Exactly.
And that's what we need.
That's right. Exactly. That
Because
can be
it
achieved.
costs so much to get things off the planet.
Yeah. But now these new materials, which I was talking to Robert also, liquid-based solar cells, they happen to be extremely cheap and very easy to produce. There are some challenges, of course, of any new perovskites. That's what you mentioned. But they have achieved conversion efficiency surpassing silicon.
Yeah,
Very easily we can achieve.
Right.
And it doesn't need very complicated technology, and we can produce right in our country.
I'm really excited about it. In kind of preparation for this, I actually hadn't pressed some of the people who I know about perovskite deployment for space.
Yes, exactly.
And the efficiency numbers, as you mentioned, are quite interesting. Obviously, the weight of perovskites is materially less, right, than
Yeah.
silicon. And as I was talking with my side is like I said, well, there's still research on radiation damage,
Exactly.
all the typical environmental things that NASA runs into. And they kind of listed through, these are the research areas that people like you need to, go do some tests on.
Right.
Before NASA could go, well, yes, it from a watt per pound, weight ratio and performance, it looks like it could be really exciting to NASA, but we got to do some tests because it needs to be robust
Absolutely.
for
I
the
think
environment.
Exactly, you're right. And people believe that that's a game-changing material.
So you're talking about perovskites?
Yeah.
So the weight goes down, right?
Yeah. And
But does the energy conversion go up?
yes,
Okay,
yes,
okay.
absolutely.
That's new. It's
Yeah,
just happening.
I've not heard that.
It's just happening.
Okay.
It's unbelievable. Right? That's the new material which can be produced from chemicals here, right here. We don't need to go somewhere else and mine those things.
And can you apply like quantum dots to that?
Yes, exactly. And you can further improve the efficiency of it. So the people have made perovskite plate. Now I was reading last week, they came up with 27%.
Oh, wow.
Yeah, it is going up. I mean, like Germany is doing a lot of research, Fraunhofer Institute and places like that. A lot of research in this area.
Okay.
Yeah.
That's good to hear.
Yeah.
We should try to work with our Western allies to leverage
That's
what
right.
they've got too. The Fraunhofer is an
That's right.
example of
Yeah.
very advanced.
Very advanced
research.
photovoltaic technology.
Now do the quantum dots, I've read a little bit about this. What happens in the radiation environment?
So see, the other thing I think Secretary mentioned, it turns out we tested the radiation hardness of perovskites. It's
Okay.
much superior than other materials. It is-
Including existing silicon?
That's right.
Really?
Yes.
Okay, I had not heard that
That's
from
right.
my team.
Yeah,
That's actually really
Yeah,
interesting.
people have tested that thing it's extremely, you have to dope, you have to add some other material
Yeah.
to that, then it becomes extremely resistant to radiation.
So let me ask you, I've had a little bit of this, but you're the expert. Could the manufacturing of perovskite films
Mhm.
be printed out of moon base or?
Oh, yes, exactly. In some ways it is better because one of the biggest problems with perovskites is humidity will affect that thing. So moon is.
Don't have to worry about that.
Exactly.
Although we did discover rust on the moon. I don't know if
I saw that, yes, yes.
So there's gotta be some humidity there.
Yeah.
So that's the environment you want. So on Earth, we have to completely do it in a desiccated kind of environment where you have to protect the perovskites from external humidity, all that thing, we have to have a chamber built for testing. Otherwise, it degrades, as a function of time.
So with perovskites, you've got higher energy conversion,
That's right.
lesser weight,
Lower cost.
lower cost, and harder radiation.
That's right. Exactly.
Hardening.
Yes,
Really?
unbelievable.
Okay.
You can read all about that thing. It's been widely researched all over the world. Yeah.
Now, tell me do we have a manufacturing issue with that in the United States?
No, I don't think anybody can do that. We can
Okay.
do it here.
Yeah, it's a technology jump from manufacturing also,
That's
right?
Yeah.
And going again to NASA missions, if there's an ability to actually manufacture this at Mars, if there's an
Yeah, it can be
issue,
done.
right? If you just had a printer for these things,
That's right.
you'd have that flexibility that could be attractive.
Interesting.
It's based on liquid, so you can basically spray that thing through an inkjet printer or some kind of printing mechanism.
Yeah.
Yeah.
Interesting. So, when we're building a space station that's going to be in orbit around the moon. And of course, that space station is going to have solar electric propulsion. So we're going to need lots of solar power.
That's right.
More solar power, more propulsion. The key that we're going to have to work on, Paul, is the transition from solar electric to an eventually nuclear electric propulsion, because that's going to be the key that gets us to Mars. I know in your talk there, you talked about the impact to the human body of low dose radiation and how you're doing some research on that. The problem right now is when you go to Mars, it's a 9-month journey. And then once you're there, the Mars and Earth are on opposite sides, or you can't get back because you're not on opposite sides of the sun, but you're well on your way. And so you got to be on Mars for a long time, and then you got to fly home. So it's a lot of radiation. So the key is if we can go faster, that's ultimately the key. If you can go faster, you reduce the amount of time that you're exposed to the radiation. We've got to do things to improve the hardening of our vehicles for sure, but photovoltaics are the beginning, nuclear, electric is the end, but propulsion is a big piece of all of it.
Yeah,
And the thing is, when you and I are thinking about how we do our programs, we need to be thinking about, if we have a solar electric propulsion system that is not designed to eventually maybe take nuclear power, we Hall thrusters, for example. We might need to think about that because that we want to go to Mars as soon as we can get there. And
yeah, I mean, I would say to the broader academic community and the commercial sector, the thermodynamic materials theory of this is relatively straightforward. The challenge, which is everyday challenge of what the administrator has to deal with, is moving from theory to actually making something that works. And I think we're at the point of I think having consensus that this is worthwhile. I know there's been some legislation. I don't know if the member is still on or not, but there's been some legislation from the Hill about taking a look at nuclear propulsion and trying to push that forward for NASA and for us to try to do that. I think we're beginning to get confidence with ourselves in terms of the impact and the possibility to start seriously looking at it. This is when we start actually engaging with academia and the private sector to talk about specific design ideas, about what the pros and cons of the different designs, which ones are more practical, which ones are more achievable, given some of the science limitations, materials limitations, and heat and so on. And I think we're kind of about the point that broadening that scope to getting input from academia and whether in materials or nuclear engineering and so on, about how we actually start thinking about specific designs and ultimately starting leading down the road of prototypes and testing.
And then the key is the manufacturing, because that's where the cost is. You can have the design that gets you the most energy efficient, but if it's cost prohibitive from a manufacturing perspective because it's just so complex, then we're back to square one. So that has to be thought of early on in the process, which is, that's where we are right now with, gallium, for example.
Yeah.
If you don't mind, I'd like to take a little bit of a kind of a 30,000 foot kind of step back when we're talking about Mars and so on. One of my themes about the country that I like to focus on is a bit on the concept of national projects and about combination of government, academia, the private sector, all kind of rowing in the same direction. And it has the impact of whatever the project or the technology is, but it has an impact on universities and education and motivating the next generation and getting people really excited about new areas of discovery. As I think about this, and we're talking about some of these points, I always think there's been four major national projects in this country, big science and technology projects. The first one was the Manhattan Project. The second one, in my count, the Apollo program. The third one was the Digital Revolution. And the fourth one we're still in the middle of, which is the Human Genome Project, the Genomics Revolution. I've thought about, okay, like what's next, right? Okay, those are big things. Looks like about every 20 years or so, something big comes along that really motivates us all as a country and as and the next generation. I talk a lot about quantum, including overlap around communications. Really the next layer of physics beyond classical physics around quantum computing and communication. That has a possibility of being a next national project. Clearly, clean energy could be another one, and new energy types could be another one. But I think it's already there that a next national project will be the administrator's Moon to Mars project, and it will take time to get from here to there, and it's moving faster than most people notice. The first rocket for Artemis circling unmanned is only barely a year out from now.
Yep.
It's not that long from now that we will have a permanent moon base, and using that as a stepping stone at the strategy of the president and the administrator on Moon to Mars. And there's a long history of challenges and debates around strategy, and he's really had wonderful leadership of bringing together different aspects of space and debates to create something comprehensive that everyone's getting behind. And all these technologies that we're talking about here today are required to kind of execute on that next kind of national project. And it's really exciting to be a part of it for Jim's and the presidents and the leadership council to have that vision and the stepping stones, hardcore engineering to get from here to there.
Yeah, no, it's exciting. Thank you for those kind words. Like I said, we can't do it without the support of the Department of Energy, and so we're very grateful for all of your leadership as well. If it's all right, I know we're about an hour. We've got about an hour and a half total. I'd also like to talk about, kind of the capability that we have in this room regarding autonomy and integrate. This is one of the big strategic thrusts of NASA, is integrating unmanned systems into the national airspace system, because it's going to be absolutely transformational for the nation. Going back to the leap ahead, people ask me, what's your biggest challenge as the NASA administrator? And people expect me to talk about a rocket launch or a moonshot, these kind of things. I will tell you that when we think about the balance of payments in the United States, when we think about the trade deficit, which my boss, the president, is very focused on the trade deficit. I don't know if you've noticed that, but he's very focused on it. There's one bright, shiny object in the American balance of payments, and that is aeronautics. We are a surplus, a huge surplus when it comes to the export of aeronautics. And part of NASA's mission is to stay ahead in that space. Now, to do that, we're gonna need to do a whole host of things to your traditional commercial aircraft. We've gotta make the cores of engines smaller to get higher bypass ratios for more fuel efficient engine. We can't make the turbines any bigger. They're already hitting the ground. Now we've got to make the core smaller to get that bigger bypass. We need higher aspect ratio wings, for example. And of course, we need hybrid electric for our big transport aircraft. If we do these things, we'll stay ahead. If we don't do these things, we're going to lose. Because you know who's investing in it heavily? Europe. We're talking about tens of billions of dollars being plowed into these technologies. And the United States of America is not investing nearly as much. So what we've got to think about is how do we stay ahead of even that? Well, number one, we're not going to fall behind in those areas. We will be able to compete. I think where Europe is looking right now, to be quite frank, and I would say this if they were in the room, which they are, because we're online and the media is watching. You know, when we think about Europe, they're looking at the, you know, our big exporter is Boeing. And when Boeing has a problem, it takes 0.5% off the GDP. That's huge. And of course, I think Europe is looking at that and they're saying, okay, now is the time to invest. We're gonna win in this marketplace. And of course, COVID was a disruptor for everybody. So I think this is a real opportunity for American leadership in aeronautics. And I'm saying that, you know, I don't take that lightly. And I'll tell you, we have to maintain our edge when it comes to these exports. Integrating unmanned systems into the national airspace system is the next big thing. And to do that, we have to have algorithms, we have to have software, we have to be able to test these configurations in all kinds of different ways. And you know, we have an industry partner here with Skydweller that wants to do just that. We've got an agency here, NASA, we have a mandate to do that. We've got a university here that has, you know, one of the, you know, I talked to our NASA aero folks. They call Lloyd Hook the golden boy. So it seems to me there's opportunity here to get some things done on behalf of the nation. Lloyd, do you have any thoughts on, you know, how would we, if we wanted to, Paul, you talked about this, the big, what did you call it? The every 20 years there's
National project.
National project.
Yeah.
If the national project is fundamentally transforming how we do transportation in the national airspace.
Yeah.
That's the question that we have to answer.
That's perfect. And that's,
Yeah.
I mean, that's what I think. I mean, I think that's the next great, technology revolution that we have in front of us as a nation. That's in my opinion, of course. But, I mean, I think it's UAS. I also think it's advanced air mobility, moving cargo, moving people between cities, that type of thing on like a smaller scale than maybe is done right now. I think there's a lot of efficiencies to be gained there. Not only that, I mean, I think the people that I work with in the FAA are very interested in improving safety on general aviation. General aviation is basically like small airplanes, and over 300 Americans died, 390 I think died 2 years ago in general aviation airplanes. That's over 90% of the aviation fatalities in the country over the last 20 years. So the same technologies that'll help us to bring in advanced air mobility, that'll help us to expand UAS to be ubiquitous, to be able to do things for the Department of Energy and the USGS and the Earth Science departments at NASA. The same technologies will help us do those things and also help us to save Americans and revitalize general aviation. Really, I mean, I think that, you know about Tesla, you know about Uber and their moves toward autonomy. I mean, I think that the same kind of issues that they're going to be struggling with in the next little bit are the same ones that aviation has struggled with maybe for the last 15 years. That now the technologies and the software, the ideas are there, they're not mature, but it's not something that will take a quantum leap in technology development for us to get there. So really, I mean, it comes down to integration, and we've been developing autonomy architectures for the last about 10 years. So integration of different systems and especially safety systems to allow autonomy. So when we worked at Auto GCAS, so what we did basically, the reason why it was such a kind of a really jump forward is we took control from a military pilot without his permission. We had to do that to be able to save him from if he was asleep or whatever, if he pulled too many G's. So we took it without his permission. We performed a really dynamic maneuver and then gave the control back to him. So it was the highest level of autonomy. I still believe it. I think it's still the highest level of autonomy in any manned production rated aircraft around the world. That's auto GCAS. And so after we got done with that project, we started kind of, some of the guys I work with at NASA, Mark Scoog and a couple of the other guys, we started thinking about, well, if we can take control from a human pilot, why couldn't we take control from an artificial intelligence pilot? And so we kind of expanded our thinking to more of like, UAS, and then the future, what's called advanced air mobility now. Can we enable these technologies to happen? And from my personal standpoint, I mean, I look forward to a time when we can all work, we can all play, we can do that while we're traveling. So that enables us to be able to really be connected in a way that I think we never have been able to in the history of mankind, right? So we with the internet and those type of things, we're able to connect on a kind of an intellectual level, but a physical level. I mean, it's just important, and that's like we've been talking about here. It's so nice to be in a room with everybody else, and so to me, autonomy helps us now with general aviation. It helps us in the future with UAS and advanced air mobility and commercial air and all this kind of thing. It also enables us to think about automobile autonomy as well, because the same type of certification is going to be required for aviation. They're going to have to deal with, and maybe it even helps us with commercial space. Because I think as more companies start to come in, you'll have to think about certification, and it's really certification of autonomy, this whole concept in general. So I think we're right there on the cusp, and I think, to me, it's like, if we could decide as a nation that we wanted to really put a lot of resources into that, I think we can make a big advancement really quick, because the technology is there and waiting to be put on. It just needs to kind of have that momentum to be built, and short time to be able to do that.
So in some of my previous talks, I like to highlight that there's 6 big areas of technology that I think we're really at the cusp of having major impacts. A lot of these kind of overlap, but the 6 I'd like to talk about are AI, quantum technologies, next generation energy, advanced mobility, space and universe exploration, and genomics. And if you think about any of those, we're kind of at the real edge of making some pretty material impacts to humanity from those. I always like Peter, but I always like kind of Peter Thiel's kind of comment he made a few years back, which was, well, the tech community promised us the Jetsons, but they gave us 140 characters. And but I did want to ask you about kind of an overlap of a specific one that I find personally interesting in the mobility area, but it overlaps with AI, which is eVTOL, right? It gets to batteries and storage, it gets to autonomy, it's mobility, obviously. It's obviously a bit of effort in eVTOL. But for making eVTOL really work, you probably want to layer in some sort of autonomy to make it really practical at the end of the day.
Yeah.
There's batteries and storage and energy density, so that you can get these vehicles to go some distance. But you have any thoughts on that topic?
Well, I was actually going to say something to you. I don't really know how the Department of Energy is involved with the power grid, but I was talking to one of my contacts at the FAA this morning, and he was talking about the fact that they're having brownouts in Southern California because of the heat wave, and what's going to happen when
I've
we
heard of
start
that. I've heard of that.
Yeah, right. So what's going to happen when we start putting electric vehicles on top of buildings that need to charge very quickly, and is the power grid going to be able to handle that type of transformation? I mean, the autonomy, the technology is there. I'm not sure if all the supporting technologies are there to be able to do eVTOL, at least in like the level that everybody wants to do it. That's one thing. Second thing, I think, as far as autonomy is concerned, it's really about bringing it to the masses. So I think that the rich can afford a private pilot, which we call, in kind of my group, we call them expert pilots. So typically, like, commercial pilots are expert pilots, and so they're very good at their job, and they have a very good safety record. But when you look at the safety record of pilots that don't have as many hours, that are a fraction of the hours of those expert pilots, not as good. So general aviation, like I was telling you, like 70% are directly attributable to pilot error, and that's with a real lack of data. So it may be more than that. So, I mean, that's just kind of the deal. To me, I feel like if we want to do something like advanced air mobility or air taxi with the eVTOL, then, I mean, really, we're gonna have to figure out a way to either make flying a lot easier and then put an envelope of protection around them as far as software is concerned, or really, I mean, I think the future to me is autonomy for that, right? To just be able to make it safe and affordable for the masses.
So when we think about eVTOL, Paul, I think there's a couple of things, and I agree with everything Dr. Hook just said. Look at a couple of companies. Lilium is one, a German company, and they're doing eVTOL right now. I don't know if you're familiar with them, but they've got a pretty robust capability that's been almost entirely funded by venture capital. I think now they're in the, maybe $400 or $500 million range as far as total funds raised. We look at another company called Joby, which is out in California. They're doing, so eVTOL, for the folks in the room that aren't in this business, it's electrical vertical takeoff and landing. So imagine a Tesla that goes from my front door to your front door, except it's vertical. So think of a taxi in the sky. It sounds very Jetsons, yeah. but we're when going back to what Paul was talking about, you talk about energy density. Like we're getting to the point where we're not getting to the point, we're there. Energy density is there right now. We have the power necessary and the mass and the volume low enough to where we can do these things. Now the question is, if you want to normalize it, which has got to be the goal, you have to be able to integrate it into the national airspace system. So right now at NASA, and I know, Lloyd, you've been involved in this, 500 feet and below is uncontrolled airspace. And so we had a project. If you have a commercial company building an electronic vertical takeoff and landing, kind of vehicle, and then you have another private company that brings with it airspace. So that the airspace management is the piece that you have to figure out. Because imagine thousands of these things operating, in my neighborhood every day. And by the way, the big investments into this right now are in fact uncrewed. We're talking about Amazon, package delivery to your front door. That's why they're investing billions of dollars into this. And the question is, can NASA use its capabilities to enable that to be a future where in your house you've got a chute, and when you order something from Walmart or Amazon, it's delivered to your door within an hour. I mean, package delivery. In fact, so 500 feet and below, we got to bring the airspace, and that would be a private company that is contracted or maybe even vertically integrated with the operator of the vehicle. But then the question is, what do you do above 500 feet? Because we're going to have to go above 500 feet for longer distances and things like that. Now you're talking about getting into the national airspace system. And the problem there is going to be certifying the vehicles. And that's where what Lloyd Hook does is so important, because that certification is going to be dependent on software that has been tested and retested and retested to the point where the FAA is comfortable with it. And if you look at what happened with GCAS, ground collision avoidance system, automatic ground collision avoidance system. The idea that the airplane will take over for you and fly away from the ground so you don't run into the ground. You take that same principle, and instead of applying it to the ground, you apply it to detect and avoid other aircraft in the sky. And then you create software that's modular, where you can have the CFIT kind of module, and you can have a detect and avoid kind of module, and then you can have a module that's thinking about the aircraft is thinking about whether or not it's going to approach a stall if it slows down too much, or whether or not maybe it's going to over G if it's turning too hard. These kind of things where you get a really smart airplane. But those are things that are at the edge of an artificially intelligent aircraft. And so the question is, could you get the FAA? Could you get the FAA to certify not on the AI in its entirety, but could you get the FAA to certify based on those parameters where you have the highest risk? And then create that autonomous environment where you can walk out to your vertical takeoff and landing vehicle and go from, one side of Tulsa to the other side of Tulsa while you're reading the newspaper. I mean, I know it sounds very science fiction, but look, with artificial intelligence and power densities, the only thing right now that is preventing this from happening is regulatory. That's where we are. You want to do research, figure out how to fix. I think, Robert, you're the guy.
So I can say that there's one branch of the service who won't even let on a large UAV, the auto ACAS function do the maneuver. So it's not technology.
Yes.
Regulatory education.
Are you picking on the Navy?
No, it's a different branch.
Okay.
But the Navy's been flying unmanned
Jim and I-
helicopters off.
Jim and I
moving ships.
appreciate that.
Navy's been flying unmanned helicopters off of ships for 13 years now. Sea State 3, Sea State 4, they can take off and land.
Yeah.
So
Yeah, that's true.
it's not tech, it's regulatory education.
I mean, once again, taking it back a little bit to 30,000 feet. This is everyday conversations that Jim and I have in our organizations. I think there's a lot of challenges in the world right now. We do a lot of COVID research at the national labs, and there's obviously lots of challenges on various different topics. But I am, and sometimes you get caught in the bubble of tech and what's aspirational. But I think what you just heard, Jim go through in detail in one little tiny area of many things going on. That's I hopefully everyone who's watching this can be inspired that there's truly exciting opportunities out there, whether you're young and looking at going to a university and what to study, or you're an entrepreneur and trying to take a look at what are the prospects and material jumps in aerospace and energy production and so on, that we get to see every day, that we talk about every day. Jim's able to talk about it without a single note in front of him, are all real prospects. And it's truly an exciting time. I would like to comment, I'd like to thank, people focus on, I think, in the popular press around challenges and negativity. There's a lot of support for Jim's program. There's a lot of support for my program. We're at all-time high support from Congress and the president.
That's true. Energy and NASA have budgets that are going up.
Yeah,
And that's bipartisan support.
so our budget is up since we've been here by 32%. I don't know how much NASA's up. It's probably even higher than that.
Well, the budget request that we have before the Congress right now would put us at about 25%.
So the ability for us to engage with universities with grants and research and programs with the private sector that we both do is at all-time highs in terms of absolute dollars. And it's grown significantly in a very bipartisan basis about that. And I think it's an obligation for our programs to perform on that additional support. But what hopefully everyone kind of feels is that there's budgetary support, there's mission, great, big vision of leaders like Jim to go after things. There's technology options that have never been thought of before that are brought about because of new capabilities of what we're able to do. And hopefully everyone kind of sees it. I want everyone to kind of see that. And whether you're kind of critiquing what government's doing, critiquing what's going on in aerospace and what the possibilities are, or if you're watching this and you're in high school and you go, well, what do I want to do with my life? Are there interesting things out there? It is truly the breadth of what we just we're discussing here today is so wide, and it's just the tip of an iceberg of things that even in our just two agencies, what we work on every day.
Yeah, absolutely. And I think, when we think about, ways for universities to get involved in our programs, I know, Paul, you at Undersecretary of Energy for Research. I know a lot of your research is done at universities. A lot of our research is done at universities. And what I hope maybe we get from this meeting, and I know there's universities watching that are not here at Tulsa, but maybe you've heard things here where your university has an alignment with what we're trying to achieve. And you can propose on projects and requests for proposal that we're going to be putting out. You know, we have a new initiative at NASA on the aeronautics side called the University Leadership Initiative, ULI. And what we're trying to do is if a university has a specific capability with that matches the strategic thrust of NASA, and that university can partner with a private company so that the research that comes out through tech transfer, the research that comes out can be put into the field right away to benefit the public. NASA wants to be a partner. So when I think about Tulsa, again, the photovoltaics capability, the autonomy capability, I think those are great niches, which is why I spent a good bit of time today talking about those. And again, all of these kind of opportunities are very competitive, but at the same time, every university needs to look at what is the talent that they have and how can it be helpful to us, how can it be helpful to the nation. And then what Paul and I have to do is we have to figure out what's the best value for the American taxpayer. And that's not an easy solution to come by. We have great people. I'm glad I'm not a source selection official. We have great people that do those kind of metrics and make those analyses. But yeah, I would encourage getting involved there. I know the University of Tulsa has had students that get engaged in our robotics initiatives, and that's been very successful. I don't think that the students at Tulsa have won yet, but I would encourage them to continue to compete, even if they don't win. It's an amazing experience to get involved in those kind of activities. So I think all that is important.
Yeah, let me just highlight just a little bit farther down the road what Jim was saying. As a result of increased support for science and technology and innovation that our agencies and the others, NIH and NSF and others have, is that the opportunity for researchers at universities to is much larger than it was just a few years ago. The dollars are there. And typically the dollars kind of happen in two buckets as a big funding agency for research for universities. A good portion of it are very targeted to areas that we're interested in. So as Jim was saying, there's certain things on Perovskites or things that are going on in advanced nuclear or quantum or AI. As a result of the strategic focal points that our agencies are doing, those funding opportunities for researchers to go do research at TU or elsewhere in the country, you can see what we're focused on. And you could probably guess that if you poke around the next year's grant topics come up, and you're in one of the areas that we're talking about, you should expect that we're putting out more money than we were before to help fund research at universities or development of technology at companies than we have. I don't know about the second bucket, and I'm not certain how NASA looks at this. We also have open calls. So we have kind of broader areas, so high energy physics and detectors of neutrinos and interstellar gammas and shape of the universe sort of stuff. Another area we didn't even have a chance to talk about here today. If you're a researcher and it's not specifically in a specific program topic that we're focused on, but it's one of the area of research that we're dealing with. We have open calls every single year. The open call dollars are higher than ever before. Once again, everything's kind of generally proportional that have increased. And so if you're a TU, you're at any university around the country, you see, I want everyone to hear, we have more support from this country because of Ranking Member Lucas and many other members of Congress and the president than we've ever had. Please pay attention to what we are doing and what we're interested in. and take a look at the funding opportunity announcements and the grants that we're putting out the door, this is an amazing opportunity for you to actually get funding. But once again, I like to come back to culture and tone, right? This is the American taxpayer, the American citizen at all-time high of supporting for the sciences. And the opportunities are there, and hopefully, whether you're young or you're old, you're getting excited about what you're hearing about and the opportunities.
I know, Dr. Hari, your programs have been funded largely by EPSCoR, is that
That's
right?
so, yeah, with Jerry and Dad, we are very fortunate to get funding for 4 cycles in a row. And
Four cycles in a row,
Yeah,
EPSCoR,
yeah,
okay.
yeah.
So the question is, how do we go from EPSCoR? How do we take that to, eventually doing bigger research projects? So,
Yeah.
and turning that into something valuable for the nation.
Absolutely. I one of the questions I posed in that solicitation, questions from the participants is that in Tulsa, we have the unique combination of 3 major universities: University of Tulsa, Oklahoma State's University at Tulsa, and OU at Tulsa. And the idea is that one university cannot have all the capabilities and resources, but if you combine the resources of 3 different universities, we can be the top-notch university.
Yeah.
So that's the combining, talent from various universities.
Yeah.
And combining, and so 3 universities are equivalent to being that of a top-notch university. So why don't we have some sort of a center here in Tulsa which can utilize all these talents from the 3 universities and then develop we don't have a national lab or national research center in Oklahoma. Right. We don't have. Idaho has it, and other states have. So why can't we have something like that where all these researchers can work on materials or some areas which you mentioned?
You're talking about like a separate institute kind of thing?
Oh,
Is that-
yeah, a center where everybody, all these people can.
Interesting.
So we were earlier with the Tulsa Innovation Lab funded by the Kaiser Foundation about how to try to create a hub around certain topics, and energy technology was one. They were talking about drones, and autonomy was another one that the Kaiser Foundation and Tulsa Innovation Lab was focused on. It was very interesting to hear about that. I think that's pretty cutting edge. We go to a lot of cities talking to them about cluster theory and technology focus points, kind of Michael Porter sort of topics. But if you don't mind, I want to put President Levitt on the hot seat. So a lot of this is of these technologies are funded by federal funding agencies like Jim Mines, my areas, and we fund people who sit here with various grant programs based on the areas of interest, and bridging the university principal investigator with a private sector development, and how universities can facilitate IP transfer startups, either culturally or structurally through technology transfer offices. Could you give a comment on how TU is thinking about some of these topics?
Sure, as the only probably non-scientist in the room, I don't know how many lawyers, I found this conversation really interesting. I was gonna go to 50,000 feet, but you're asking me to go a little lower, so I'll start there and maybe end higher. So I think this concept of the triangular relationship between government, private sector, and higher ed is really key to the future of research at places like the University of Tulsa, where we're not a huge R1 research institution. I think Dr. Hari suggesting that we pull resources together is really, really important. And we're actually engaged in a project like this right now in cybersecurity, with the intersection of a private sector company in lieu of government there, philanthropy, in particular the George Kaiser Family Foundation and our computer science department and our engineering school to accelerate PhD production in sort of the private side of cybersecurity. As you know, the University of Tulsa has a historic niche in the national security side of cybersecurity and has partnered with the NSA and with different agencies for a really long time. So this is really, really critically important. And we had a conversation last week with a couple congressional delegations. And one of the things that I think universities need to do better on is infuse within traditional research offices some just commercialization expertise, even just like working with faculty on how to give the elevator pitch about their technology, or sort of how to take the theory of what they're doing in their labs and sort of translate that into a more commercializable soundbite. I know the faculty in this room well. I'm sort of envious of the technical and scientific knowledge behind all of their work. And I know that they all really would be really wonderful at doing that and making that transition, but we haven't really focused in academia and in traditional research offices to be able to do that. So that's sort of the specific answer. I am going to go up to 50,000 feet for a minute, if you don't mind, because this is a disruptive moment in higher ed. Right, we all know that we were sort of there. We were there anyway, and COVID accelerated it. And I can't imagine how many articles and pieces have been written about sort of the end of higher ed, the death of higher ed, and really what I hear today is something just much more positive and encouraging, and sort of the excitement of how higher ed can intersect with these national project moments. And with that tripartite relationship between, the government, the private sector, and higher ed, and I think for us in higher ed, we have to become a lot less territorial about working together, as Dr. Hari said. So even within that, to sort of get out of our own silos and realize that we're better together. And as the non-technical person in the room, there was so much that I heard today about the regulatory framework, sort of how we think about risk, how we think about managing risk, that one of my takeaways is that even for students, and I just dropped off my daughter for her first year in college, even for students who aren't STEM oriented, like neither of my kids are STEM oriented, having a fluency in sort of STEM and technology and science is just going to be so important to be able to be successful in every area, and likewise those who are really steeped in it to sort of be able to communicate well, to translate ideas well, and to be able to really write well. I think that's what sort of institutions like TU who do both the science and the liberal arts really well add to the formula. So I just want to thank you all. Thank you for letting me go 50,000 feet and a little lower there.
Well, it's fantastic. I'll tell you, if it's all right, President Levitt, I'll just echo the triangle. The reason it matters to us is that, if we turn to a private company to have something produced directly, we can get something produced. What we find as an agency, though, is when we go to a university specifically, NASA, we're trying to do science, but it requires engineering to do the science. And so when you do these projects, you get a lot of times when you go straight to a company, they're going to want to do the engineering and they're going to want to deliver a product, but they're not working day in and day out with the scientist. When you do a project at a university, you get the scientist and the engineer actually working together side by side, day in and day out. And the value of that is that you can give them a cost cap and you can give them a deadline and they meet it, because they make trades. As they work together, they make trades. The engineer can say, well, we're running into a roadblock here. It's going to cost us a whole bunch more money. what if we did this instead? And the scientists can say, yeah, that works for us, or it doesn't work for us. And they make those trades early in the development process, and you get this cycle of staying on budget and on schedule. Then the biggest value, and the reason universities are so important in this triangle, and I know Dr. Hook and Dr. Hari can attest to this, the students get involved. The students are the ones doing the work. You'll have a principal investigator that's a faculty member, but you'll have students that are actually graduating, and they're not just learning chemistry, calculus, and physics. They're graduating with hands-on experience, developing the very things that NASA is going to need them to develop when they go out into the real world. And so that's why a lot of these projects, we go to universities because that's how you engage the next generation. And so I'll double down what you said. We're very committed to that triangle. We're very committed to making sure that we are graduating. I think you said production. We're producing PhDs. That's something that we need to do more of, especially in the STEM fields. We're short. We need more. And so it's good to hear you say those things, and we're grateful for you hosting this today. I know we're over time, so I'll stop talking.
I mean, maybe another word kind of ending up here. Once again, I'd like to thank President Levitt for having us here. It was good to be back in Oklahoma with a number of the science leaders of this country are from. Think things are very exciting. It was very worthwhile me hearing about some of the exciting things and verification with some additional data on some technologies that we certainly heard are moving down the road in terms of specific applications. So it was worthwhile hearing about some of these very specific points. But it was also, I think, great to hear and to talk about. Hopefully everyone kind of also heard from our perspective about what we think is going well right now and about how exciting things are right now. And hopefully I got a lot out of it, and hopefully everyone else here, as well as people who are listening virtually, also got quite a bit out of that. Glad we could be here. Thank you for hosting us.
Thank you so much.
It was a very exciting day, and I'm glad that Jim and myself scheming to get together and have this and doing this here, that it worked out so well.
Thank you so much.
Thanks so much.
Well, thank you, guys. It's been good. And we will, President Levitt will stay in touch and figure out, kind of areas where we can work together.
Sounds great. Thank you so much. It was a pleasure.